I welcome you for the session number 9 on the chapter interference. Here we shall discuss about the Michelson's interferometer. Okay, Michelson's interferometer. Michelson's interferometer consists of two highly polished mirror M1 and M2 and two plain glass plates A and C arranged as shown in the following figure 1. The rear side of the mirror A is off silvered so that light from the source S is equally reflected and transmitted by it. Michelson's interferometer, the ray reflected from M1 passes through A thrice, while the reflected ray from M2 passes only once through A. To compensate this optical path, a glass plate C of the same material is used. Light from a monochromatic source is rendered into a parallel beam by passing it through a lens L is made to fall on the plate A, inclined at an angle of 45 degree to the incident light. The light is partially reflected along AM1 and partially transmitted along AM2. These two beams moving mutually perpendicular to each other are reflected back the mirror M1 and M2 and retrace their paths and reach the plate A. The ray reflected from M2 is again reflected from A and the ray from M1 is transmitted through A, and these two rays travel along the same direction and are received by the eye. The mirror M1 is fixed on a carriage and can be moved with the help of the handle H. The distance through which the mirror M1 is moved can be measured with the help of a micrometer screw attached to the handle. The plane of the two mirrors can be made perfectly perpendicular to one another with the help of the screw attached to them. The plate C is necessary for white light fringes and can be dispensed with while using a monochromatic light. If the mirrors M1 and M2 are perfectly perpendicular, the observer's eye will see the image of M1 and M2 through A. There will be an air film between the two images, and the distance between them can be varied with the help of the handle H. In this case, the fringes will be perfectly circular. If the path traveled by the two rays is same, then the field of view will be completely dark. If the two images of M1 and M2 are inclined, the air film between them has wedge shape and straight fringes are observed. Here, circular fringes. There are types of fringes. For circular fringes, when the mirror M1 and M2 virtual images M2 dash of the mirror M2 are exactly parallel, in general, circular fringes are formed. In this case, the source is extended 1 and S1 and S2 are virtual images of the source due to the mirrors M1 and M2. If the distance between the M1 M2 dash is equal to d, then the distance between S1 and S2 is equal to 2d. The path difference between the beam will be 2d cos theta. When 2d cos theta is equal to n lambda, the beam will reinforce to produce a maximum. These fringes are circular and are formed due to phase difference determined by the inclination theta. They are known as the fringes of equal inclination of Heidegger's fringes when M1 and M2 dash are coincide. The path difference becomes 0 and the field of view is perfectly dark due to path change occurs for the one beam due to reflection at the denser surface. When the mirror M1 and the virtual images M2 dash of the M2 are inclined, the air film enclosed is wedge shaped. The fringes formed depends upon the nature of the inclination of the two mirror images. If the two mirrors intersect at the center, the fringes are straight and parallel as shown in figure. If the mirrors are inclined to one another and does not intersect, then the fringes are curved with the convex towards the thin edges of the wedge. White light fringes. With white light, the fringes are observed only the path difference is small. The different fringes overlap on one another and only a few colored fringes are visible. The central fringes is dark and few fringes near the central dark fringe are colored. After about 8 to 10 fringes, a number of colors overlap at a point, and as a result, general illumination is observed. White light fringes are useful for the determination of zero path difference between the interfering rays. It is useful in the standardization of the meter scale. Okay. Let us discuss about some of the questions on the session. First question: the device used in the Michelson-Morley experiment was dash. Option A, telescope. Option B, plane grating. Option C, interferometer. Option D, prism. The answer is interferometer. In interferometer, the Michelson-Morley experiment was used. Okay. The second question: the fringes are equal inclination produced by the using a Michelson interferometer are called as dash. Equi-inclination fringes. Option B, Michelson fringes. Option C, Edinger's fringes. D, Morley fringes. Answer is option C, Edinger's fringes. Okay. Thank you for patient listening.